Welcome to the NPTEL lectures on techniques and principles of modern radar systems. So, we have in previous several lectures we have seen match filter, then the various correlation properties etc., and we have discussed about resolutions. Then finally, we have seen how to improve the range resolution, pulse compression etc. So, all those are detection in radar receiver. So, today we will see some tutorials on that. The first problem is this: detect a rectangular pulsed CW waveform has a center frequency of 1.25 gigahertz, a pulse width of 5 microsecond and a PRF of 400 hertz. Find the bandwidth of the radar signal, the spacing of the spectral lines, give a qualitative expression for the spectral envelope. Now, the radar waveform is modified, so that there is a linear frequency sweep across the pulse. At the start of the pulse, frequency is given, and at the end it is so and so. Find the new center frequency, bandwidth, spectral line spacing and approximate shape of the spectral envelope. So, simple problem, just you will have to know the basic definitions, and that we will be seeing. So, this is the first problem. So, what is the spectral main lobe bandwidth? Spectral main lobe bandwidth, that we know roughly. This is not the resolution type of thing. So, roughly I can say it is 1 by tau. It is a constant frequency pulse. So, 1 by. So, tau value is given 5 microsecond. So, it is 200 kilohertz. Now, then the question is what is the spacing of the spectral lines. So, spacing of the spectral lines will be obviously in a pulse radar, if you have pulse repetition. So, at every PRF things you will have a spectral line. So, we can say that spacing of spectral lines, they will be 400 hertz. So, every 400 hertz you will have a spectral line. So, we have lines at, you can say first is 1.25 center frequency. So, 1.25 minus that 400 hertz. So, 0.0000004 into 2. So, that will be 1.2499992 gigahertz. Then there will be 1.25 minus this thing into 3. Or you can say that this is 2, or lower side if we see it will be, you can say into 1. So, that will be something 1.2499996 gigahertz. Obviously, 1 at 1.25 gigahertz. Then there will be plus 1, so 1.25 plus that into 1. So, that will be 1.25 0.00004 gigahertz, then this into 2, so 1.2500008 gigahertz, like that, this side also. So, there will be spectral lines like this. Then come to 3. What is the question here? That give a qualitative expression for the spectral envelope. We know it will be a sinc function. So, spectral envelope will be something like sin pi f minus f c tau by pi f minus f c into tau. So, that means in our case this will be sin pi f minus 1 250 000 gigahertz into 5 into 10 to the power minus 6 divided by pi into f minus 1 250 into 5 into 10. So, this will be the shape. Then let us come to part D, that what was the problem. Now, the linear modulation is given. So, what is the new center frequency? Part D is new center frequency. So, we can say f c is AM of f mean and f max. The new center frequency is something like this. So, it is 1.2475 plus 1.2515 by 2. So, that is 1.2495 gigahertz. That is all. So, part D is over. Then we will have to do part E. What is part E? The bandwidth. So, okay. Bandwidth is now independent of pulse width. That is the new thing, that LFM that makes it is independent of pulse width. So, what will be the bandwidth? You see, previously it was dependent on the pulse width, but now it is independent of pulse width. So, it is 1.2515 minus 1.2475 gigahertz. So, that comes to 4 megahertz. So, previously it was 200 kilohertz, now it has increased, but it is not dependent on the pulse width. And F spectral line spacing. So, spectral line spacing in the new case. So, that will be same as PRF, because PRF will make that every 400 hertz it will have its signature, and spectral envelope, we have seen that LFM makes roughly this rectangular. So, it will have something like this. So, you can say spectral envelope is roughly a rectangular. There will be some ringings that we have seen, that this is spectrum. Okay. So, this problem was easy. Now, let us go to the second problem. This is a classical problem. Find the match filter frequency response function for a perfect rectangular video pulse of duration tau and amplitude A. Assume the pulse extends in time from minus tau by 2 to plus tau by 2. Take additional time delay. A match filter requires a time delay, but assume that is to be 0. Then sketch roughly the magnitude portion, magnitude frequency response, sketch magnitude this transfer function of the match filter. In part C, sketch roughly the output of the video match filter as a function of time. That means the match filter output. Now, in D there is some your expression for HF probably contain non-zero values for some negative frequencies. What is the meaning of negative frequency in HF and what happens if we remove the negative spectrum completely? It's a good conceptual question. So, we will see that. I think this is now problem 2, tutorial 6. So, we know, let us say the signal S t is this is 0, this is A, this is minus tau by 2, this is plus tau by 2. So, I can easily draw what will be S of minus t 0. So, for a rectangular function it is good, it is not changing. So, I can say that my H t, the impulse response of the match filter, that will be also like this, that 0 tau by 2 minus tau by 2. So, I will have to now find the HF. So, HF is minus Fourier transform H t e to the power minus j omega t dt. So, this is, it exists from minus tau by 2 to plus tau by 2. H t's value is A. So, it is A e to the power minus j omega t dt. So, this we know simple to integrate A tau sinc pi f tau. So, as easy as this. So, in part B we are asked to find the magnitude part. Obviously, this is the thing. So, magnitude will be, I can write H f magnitude. In general, this is a complex quantity, but in this case it is not a complex quantity. So, magnitude will be sinc function, since we are putting the magnitude. So, there will not be negative signs, negative portions like that. Here will so, this is H f, this is F, this is 0, and we know these points are 1 by tau, this point is 2 by tau, this is 3 by tau, etc. Similarly, minus 1 by tau, minus 2 by tau, minus 3 by tau, etc. So, this is a sketching of the magnitude portion. Then let me again check what was the sketch roughly the output of the video match filter as a function of time. That is the next part. So, this will require, this is also simple, but you will have to meticulously do it. So, ST is coming, HT now we know, we will have to find YT. So, what is YT? YT is ST convolution HT. We know what is convolution, minus infinity to infinity, S, make a new running variable, S lambda, H t minus lambda d lambda. So, now there will be several cases. First case 1 is t is less than minus tau. We will take case 2 as t is greater than plus tau, and case 3 is minus tau less than t less than tau. Okay. So, the total integration will be, so first let us see what is case 1. T is less than minus tau. So, that means I have S lambda, this is my lambda, minus tau by 2, tau by 2 0 a, and what is my H t minus lambda versus lambda. So, t is less than this, that means I have something here. So, this is my here. So, you see that roughly this is minus tau by 2. So, it is here. So, we can say that if I multiply y t will be 0 here. So, case 1 does not give me anything. Similarly, case 2 I have t is greater than tau. So, again I can S t is as before, not S t, S lambda, because running variable has changed. So, this is also lambda 0 minus tau by 2 to tau by 2 a, and what will be H t minus tau, this is S lambda, that lambda minus tau, this is lambda. So, it will be somewhere here, this is a. So, again I can say y t is equal to 0. So, case 1 and case 2 are out of my A. Case 3, this will give me something. What is case 3? Minus tau less than t then plus tau. So, there are two sub cases. I will have to break it into sub case A. One will confuse. So, sub case A, that 0 is less than t less than tau. So, put what is S lambda h t minus lambda, this is lambda. So, okay, this thing is A, and somewhere here is tau. So, what is this? This point easily we can see t plus tau by 2, and what is this point? This point is t minus tau by 2, and somewhere here will be minus tau by 2. So, we can see that from here to tau by 2 there will be multiplication. So, we can say y t in this case will be obviously 2s. So, s square, but then this lower point t minus tau by 2 to plus tau by 2 d lambda. So, that will give us s square t minus s square not t, s square tau minus t. You do it. Then let us come to case B, sub case B. Sub case B, that is minus tau so again as before, S lambda, this is lambda A minus tau by 2 plus tau by 2 0. So, here it will be something like this. Let us say this. Here will be tau by 2. So, this is h t minus lambda A. Then this point obviously will be t minus tau by 2. Somewhere in middle there will be minus tau by 2, and this point is t plus tau by 2. So, obviously, from minus tau by 2 to t plus tau by 2 we will have the multiplication. So, y t will be s square minus tau by 2 to t plus tau by 2 d lambda, that will be s square t plus tau. That is all. So, now I can write, putting all those together, y t is s square t plus tau minus tau less than t less than 0, s square minus t plus tau is 0 less than t less than tau and 0 otherwise or elsewhere. So, I can now sketch this y t versus t. So, you can see t plus tau, a square is a constant, that is nothing, t plus tau, that means it is a linear function. So, s square tau, here it is 0. So, this will come down, this will be linear, this is tau and this is minus tau. This is the shape. Now, next part is that negative frequency. Actually, you know that negative frequency concept started from Fourier, because we are taking transfer function etc., those are Fourier transform. So, for mathematical soundness, because Fourier tried to break a real signal into its eigen components, and that is why the complex things came, and that also introduced this negative frequency concept. So, this negative frequency concept does not have the physical meaning, but for mathematical reality it is there. Now, it is well known that if we chop off the negative spectrum, then the signal will no more be real, because half of the power is in the positive spectrum, half of the power is in the negative spectrum. That makes the whole signal thing real. If we cut off the negative thing, that we cannot do, but you know that we can do that. Complex envelope concept is there, which actually shifts the whole spectrum to the positive side. So, if you are uncomfortable with the negative side, you can work with the complex envelope, which we do for band pass signals, but otherwise the physical meaning of negative frequency is not there. Spectrum is a mapping. So, in that map, mathematics dictates that it does not have any physical meaning. Okay. I think this problem we have seen. Let us see the last problem. This is a problem. A C-band ballistic missile detection radar employs a linear FM pulse compression with a 1 millisecond uncompressed pulse width, having a down chirp covering a bandwidth of 200 megahertz. If the target has a radial velocity of 2 kilometer per second and the radar mistakes that as a range information, because target has a velocity, but radar is mistaking that as a range information. What will be the error in range due to the Doppler shift of the target? What is the range error in terms of the resolution of the compressed pulse? Good problem. So, first actually let us see the solution. So, this is tutorial 6, problem 3. So, first find out the Doppler So, radial velocity set, the frequency set. So, we can calculate this will be 73.33 kilohertz. Now, first is you see the due to LFM the transmission frequency changes by 200 megahertz in 1 millisecond. So, how much time it will take to change it to 73 in 11 by 3 into 10 to the power 7 second. So, we can say that delta tau, that is 11 by 3 into 10 to the power minus 7 second. So, we can say that this will be given the range error correspondingly. So, range error delta r will be C delta tau by 2. So, that will be 55 meter. Now, range error is so actually radar is mistakenly thinking that as though the frequency is changing, radar is thinking this is due to Doppler it is having. So, that is why the range error is erroneous. Now, that is okay. I think I will have to increase the page. And part B, the compression gain of the LFM, compression gain I, that we know is given by B tau naught, and here B is 200 in megahertz and tau naught is 1 millisecond. So, it is 2 into 10 to the power 5. So, now we can say without LFM range resolution was how much? Let us call it delta R1, that was C by 2 into 2/3. Here we are taking the exact value of resolution. So, if you put this, it will come as 100 kilometer, and with LFM range resolution will be, let us call it delta R1 by the compression gain. So, that will be 100 by 2 into 10 to the power 5. So, it is 50 into 10 to the power minus 5 kilometer, a drastic improvement. So, now we can calculate what is the range error divided by compressed pulse range resolution. That will be, range error was 55 meters. So, that is 0.055 kilometer. This also is 50 into 10 to the power minus 5 kilometer. So, that will be 110 range cells. So, it will, this error will lead to 110 range cells, the range will change. So, this is something that if you use LFM, this should be aware that you are having a frequency change, otherwise it thinks that that is due to the Doppler, and that makes the range calculation difficult. This is the concept of range migration type of thing. Okay. So, good problems. So, with that, the detection in radar receiver we have seen. In finally, when we will see the statistical theory, because there are the environment, there are statistical fluctuations. That time again we will revisit this radar detector. That will be in a future tutorial. There we will again come back here in the detection theory. Thank you.